All right, let's look at this problem called shortest path visiting all nodes. So what are we given here? So we're given an undirected connected graph, and the way it's given is the adjacency list representation. That means graph of I is a list of all the nodes which is connected to the ith node, right? So for example, in this graph, this is how it's given. Node 0 is connected to 1, 2, and 3. Node 1 is connected to 0. Node 2 is connected to 0. Node 3 is connected to 0, right? So just the adjacency list representation. And what we have to return is the length of the shortest path that visits every node. Okay, so we have to start from some node and at some node, and you have to visit each and every node. So, okay, and it says this, you may revisit node multiple times and you may reuse edges. For example, here, if I start from 0 and if I visit each one node exactly once, then I cannot traverse the node from 0 to 1 or 2 to 3 and I'm stuck. But this is where it says that you can reuse the edge on and you can revisit the node. So for example, if I start from 0, I can go from 0 to 1, then back from 1 to 0. Then I can go from 0 to 2, back from 2 to 0, and then from 0 to 3, right? Now, this is from 0, but this is when I start from 0. So for example, if you look at it, in this case, if I start from 0, so the path can be 0, I go to 1, and then I come back to 0. Then I can go to 2 or 3 either. Let's say I go to 3, I come back to 0, and then I go to 2, right? This is a path. But say if I start from 1, then I could just follow this much path, right? From 1 to 0, and from 0 either to 2 or 3, and then back to 0, and then the other one, right? So we have to find the shortest path. And when it says shortest, we can do BFS, right? Um, and so the shortest path can start from 0, can start from 1, can start from 2, can start from 3. So like a multi-source BFS. So when you start the BFS queue, all the nodes that can be a possible starting point, just add all of them into the queue. That's the multi-source BFS. But there is one problem. In BFS, you maintain a visited array, and visited array so that we don't traverse we don't visit the same node again. But that's not. But that's the problem here, right? Here the problem is from 0 you go to 1. From 1 you can go back to 0, but 0 is already visited, right? And so okay, you say okay, then I can, but it is allowed, so I don't track visit it. But then it's possible that I can just keep oscillating between 0 and 1, right? Yes, from 0 I can go to 1, and from 1 I can come back to 0. But then if I go again from 0 to 1, and it's a repetition, like it shouldn't. So you have to figure out what visited means here, right? So for example, so from 0 you go to 1. From 1 you can come back to 0, because from the 0 you can go to somebody else. But from the 0 you cannot go to 1. So this is not allowed. And how do we track that? Like that's the bit. How do we track uh, which visited part is allowed or which visiting part is not allowed? So forget about this. This is a simple case. Let's say I start with 0, 1, and let's say 2, and then 0, and then 1, and then 3. Okay, let's say this is one path, right? There's another path, let's say 1, 0, okay, 1, 0, say 2, 0, 1, 3. Now, I can even reduce it. Just take it till here, just take it till here. Now, both these paths, I should only consider one, right? Because what has happened, because what does this path means? It says I end at 0, and the nodes visited are 0, 1, and 2. This guy say I end at 0, and nodes visited are 0, 1, and 2. Rather, I can say even I should have stopped here itself. The ending node and the exact number of nodes and then the nodes that are visited, if those are same, then you don't have to consider this path, right? Like 0, 1, 2, 1, 0, 2, it's all the same, correct? So how do we track that? So we maintain a map or a rather a bitmap or a bit mask indicating the visited nodes, right? And for if every last node, we'll maintain a bit mask visited nodes. That is, so what I mean by that is, so what I mean by that is this. So when I start with 0, I will maintain for when 0 is the current node, a path which just traversed 0 has been visited. Then from 0 I go to 1. So 1 is the current node. So for 1, a path ending at 1, a path ending at 1 is there, which contains nodes 0 and 1, right? And now from this 1, let's say I go back to 0. So this is allowed. This is allowed because this ends at 0 and it contains a path. It contains nodes both 0 and 1, right? So it's a unique one. Now from this 0, if you go to 1, so you say I'm ending at 1, and what are the nodes that are connected? What are the nodes that have been visited? 0 and 1, which is already there. So this path I am not going to take. And let's say I take a different one, 2. So 2 is a different one. So for 2, I have a path which consists of nodes 0, 1, and 2, right? That's the idea. So that's the sort of mapping that will try. And here, instead of keeping this mapping like a list on array, this mapping will keep as a bitmap, right? That is a bit that we use. And bitmap is basically we'll have a map like an integer number on which bit number 0, bit number 1, and bit number 3 would be set in this example. So that's one idea. So that is the kind of visited that we'll have to maintain. Okay. So let's say what does visited mean here. So let's first get the size of the array or the number of nodes. So graph.length. So we maintain a visited, and now I can maintain like a set, right? I can maintain a set, or what I'm doing here is I'm just maintaining all combinations. So for each node, what are the different possible? Um, okay, so new boolean. So for each node, what is the size? How many different combinations of maps? How many different maps can exist? Well, what are the different combinations of n nodes, right? 2 raised to the power n, so which is this. So this is my size. So what I mean by this is, uh, so what I mean is this. So for a path ending at 0, how many different nodes, how many different combination nodes can be there? Let's say if there are uh, 10 nodes, right? Then it's possible, then you have 10 bits, and each bit could be set, right? And so there are different, for each bit, there is 10 combinations. So for each bit, there are 2 combinations. So 2 raised to the power 10, right? 2 times 2 times 2 times 2, right? So not, and which can be represented by 1 left shifted n times. So this is how many different combinations of visited nodes can be there, and you consider all of them. And yes, we can also maintain a map, but here we are given that n is just 12, so 2 raised to the power 12, that's the size. And it, like if we maintain a set, then it might take cause a TLE or something like that, but this can be better. You can directly get the answer. So that's bit one. Now you said you will maintain a queue. Okay, so what will the queue contain? Now again, for every node, you also need to maintain for visited. We needed to maintain this. So we can call it a mask or something, right? So for each, so we need let's say, okay, integer array. So q integer array, let's call it q equals to new necklace, and let's first add. So why integer array? Want to because I want to check visited, right? So I want to know for this node, which is the mask, which is the list of nodes that I have traversed, or which are these nodes at this point. I want to maintain that as well, so that's where I can get that and check whether it's visited or not. So for multi-source BFS, so basically add all the nodes. So for I equals to 0, less than n, plus plus, you go q dot add. What are you going to add to the queue? So you are taking integers, so new int, well, I, and this will be the mask, right? 1 less than I. So that means I have a path which ends at this node, and this represents the mask of nodes that have been visited. In this case, it's only one node, right? So this all gets added here. And now, while, okay, let's also maintain like a level. Initially level is 0. And now what do we do? So get the size of the queue, or rather we can call it level size, right? So at this particular level, at level 0, all the nodes were added. So is uh, answer for I equals to 0. And so what do we do? Well, first you pop it out. So you remove and you go, okay, what is the node? So the node is array 0, and what's the mask of visited nodes? The mask of visited nodes is array of 1. Okay. So now what are you going to do? Well, if this mask of visited nodes is equals to all nodes, right? Which is what? If this is equals to this, no, this is not. It's not all nodes. So okay, let's call this all nodes mask is what? It is this minus 1, right? So for example, if there are 3 nodes, 1, 1, 1, which is what? 2 raised to the power 4 minus 1, right? No, if there are sorry, yeah, if there are 3 nodes, then it's 7. 1, 1, 1 is 7, right? So 2 raised to the power 3 minus 1. So it's this. So it's called all nodes mask. Then you have already found the shortest path. This is the shortest path, right? So what do you return here? You return, so level will tell how many nodes are there in the path, right? Initially it was 0, and so do you return level or return level plus 1? I just you just return level, yeah. So you return level. Cool. So this is that, and because you can see here, um, 1, 2, 3, 4, 5, the path, it's counting the number of edges, right? So that's why initially if it's a single node, which will be the first case here, then it would just return 0. Okay, and if that's not the case, if then what do you do? Then you generate the new mask. So what is the new mask? New mask is whatever this mask was. Okay, so you basically you add all the consider all possible nodes. So uh, for each neighbor in graph of node, right? These are all the neighbors it has. Then you generate new mask. So new mask will be mask of visited nodes, and in that you add neighbor. Okay, so this is a new mask. Now what you have to find is this new mask, is this set of you can maybe even change. Now yeah, you have to new new mask. So if this new mask is a list of nodes that have been visited, ending with this neighbor is already exists, then you don't want to consider it. You want to consider it only if it is not visited, and which is visited ending at this neighbor with this new mask. Have you already visited through some other path? If yes, then you don't want to consider it. And if it's not visited, then you want to consider it. Then you want to do q.add new int, and you want to add neighbor, and you want to add new mask. right? And at the end of this for loop, rather at the end of this for loop, you would say level plus plus, and you know that there would be a path which would return also. At the end of the day, like this while loop, this return at some point will happen. But just for compilation perspective, you might want to add just a return minus one here. So that's the entire logic. Let's run the code, fix any compilation errors. Okay, submit. Okay, might be some issue. So we did get a time limit exceeded. Let's see how we can fix it. Okay, 40 test cases passed. So we have a boolean, we have a queue. Okay, I'm hoping the default value of visitor is false. Oh, I'm not setting visitor as true. I'm not setting visitor as true, right? So yeah, I think that's the problem. If not visited, here also. So you do visited of I, so true, and similarly visited of neighbor and okay. Run again and submit again, and it gets accepted this time. All right.